Welcome to example number 6. Here you're asked to calculate the rotational inertia of 4 masses. You can see over here in the diagram you have mass here of 3 kilograms, 2 kilograms, 4 kilograms, another 2 kilograms, and they're centered along in this XY plane. And then we're going to be rotating it along the z-axis. Kind of maybe help understand or visualize this, I've created a quick little animation to show you what this looks like. And here's a quick animation of the object. So I'm basically rotating them about the z-axis that you can see here, and it's rotating along the xy plane. So we want to find the rotational inertia of this system. So if you recall, the rotational inertia of a point mass is basically given as I equals mr squared. So if you have several point masses, then you simply just add them all up. So it's just the sum of all the mr squared terms. So for this problem, all you really need to do is you have, say, m1, we'll call the 3 kilogram one here, m1 times r1 squared. And then we have also m2 times r2 squared. We have also m3, right, times r sub 3 squared. And we have lastly this 4 kilogram mass, that's our m4 times r4 squared. Now, what is r? Well, r is the distance from the axis of rotation to where the mass goes. So this is r. So if we draw a quick little triangle here, and so I've just drawn it over here, so you can see that hopefully this distance, which is totally of 6, so half of that would be 3 on this side, and then half of this one, which is 4 meters total length, that's going to be 2. So that means the radius is basically, using Pythagorean theorem, 2 squared plus 3 squared, which is really just the root of 13. So, hopefully you notice that basically r in all of these situations here are all the same. So you could really take out a common factor of r in here and say it's really just m1, m2, m3, m4, and then multiply by all the same common r of root 13. So we simply are going to add up the masses of 3 kilograms, 2 kilograms, 2 kilograms, and 4 kilograms, and multiply by root 13 squared. Okay? And this will give you an answer of 143, and these are all in kilograms, and this is in meters being squared, so multiplied by meters squared. And that's the units of rotational inertia. Okay, interesting, by the way, would be, like, I could have asked, didn't have enough space in this question, but to say if I were to rotate the objects about a different axis. This is rotating about the z-axis in the xy plane. Could have asked, for example, to rotate it about the y-axis. That would look like something like this. I just changed the program, so now it will oscillate around the y-axis. And so now the radius would be different, right? It'd be rotating at a radius of 2 away from the y-axis. Or you could even rotate it about the x-axis, as shown by this little animation here. Where is it? Here. And I'll run it again. There we go. So that's actually the object's now rotating about the x-axis, and now here the radius would be actually 3. So there's obviously different axes of rotations that you could rotate a system about. So hopefully this kind of makes sense. I've only done it along the z-axis in this problem that was presented, but it'd be interesting to also do it along the x-plane, x-axis, or y-axis. Okay, and that is it for this example.